Welcome to this explainer. Today, we're diving into a mind-bending physics experiment that absolutely defies everyday logic. We're going to look at a beautifully simple demonstration where a cheap $5 cat toy laser pointer can completely shatter our classical understanding of reality. So if you think you know exactly how light behaves, well, get ready to have your intuition flipped totally upside down.
Picture this simple setup for a second. You've got a green laser firing directly down toward the front of a room. It passes right through a narrow, adjustable slit, and the resulting laser dot is projected directly onto a blank screen or wall right behind it. It's a super straightforward arrangement, right? But the crucial part of this whole setup is that the slit is adjustable. We can physically make it narrower or wider just by pushing the edges closer together. Now, it might seem like common sense, but I want you to actively predict what happens to that projected laser spot as we physically make that slit tighter. Seriously, imagine watching that green dot on the wall. If you close the physical gap that the light is shining through, what does your brain tell you should happen to the light hitting the wall? You'd probably guess that the dot just shrinks right along with the slit, wouldn't you? Okay, let's dive into this, because this is where reality gets really weird. Step 1 actually goes exactly how you'd expect. As the slit starts to close, the spot gets narrower. The sides of the beam are simply getting cut off by the physical edges of the slit. Makes complete sense. And honestly, if you stopped right there, you would never realize that a fundamental quantum law is at work. But if you keep going, something incredibly strange happens. As you make the slit a tiny, microscopic fraction of its original size, the spot on the wall violently spreads out. I mean, isn't that incredible? You are actively restricting the physical space the light can pass through, and yet the resulting beam on the wall is getting remarkably wider. Section 1. Heisenberg's formula explained. So, to understand why making a hole smaller somehow makes a beam of light wider, we have to look past everyday physics and dig into the foundational rules of the quantum universe. We need to talk about Heisenberg's Uncertainty Principle. It's a foundational concept in physics, normally written out as delta x times delta p is greater than or equal to h over 4 pi. In plain terms, it states that you can never, ever simultaneously know both the exact position and the exact momentum of a particle. There is a fundamental, unbreakable limit to how precise we can be about those two properties at the exact same time. Let's quickly break down the alphabet soup here. X is the particle's position, literally where it physically is in space. P is its momentum, which is essentially where it's going and how fast. The delta, that represents our degree of uncertainty in those measurements. And the golden rule here is that when you multiply those two uncertainties together, the result must always be greater than or equal to that value on the right, which features h, famously known as Planck's constant. For our purposes today, the absolute most important thing you need to know about h, Planck's constant, is that it is a ridiculously small number. And that perfectly explains why we don't bump into this spooky uncertainty relation in our day-to-day lives. Everything we interact with, cars, baseballs, our own bodies, is astronomically bigger than h. You don't suddenly blur into a wave of probability when you walk through a narrow doorway. But when we scale way down and deal with something incredibly tiny, like the photons in our green laser beam, this mathematical limit suddenly becomes a very real physical barrier. Section 2. Physics in action. Let's see how this concrete math actually translates to our incredibly strange laser experiment. Think about what we were physically doing with that adjustable slit earlier. As we pinched that gap closed, we were actively decreasing delta x for those photons. We were reducing the uncertainty of their position, essentially forcing them into a highly precise location in space as they squeezed through. But remember the formula. The two uncertainties multiplied together must be greater than or equal to that constant limit. So, at a certain point in narrowing that slit, the tension builds, and you hit this absolute quantum wall. If you restrict that gap any further, you are fundamentally going to break Heisenberg's uncertainty relationship. And here is the crucial point. Nature absolutely will not allow that rule to be broken. To ensure we don't violate Heisenberg's uncertainty relation, something has to give. Because we force the position uncertainty so low, the uncertainty in the momentum, specifically in the horizontal direction, has to go up. So what does an increase in horizontal momentum uncertainty actually look like in real life? Well, it means the photons that were previously flying perfectly straight must now randomly veer off to the left or to the right. The more you decrease the uncertainty in position by narrowing the slit, the more the uncertainty in momentum has to skyrocket. And because these photons are now traveling left and right, it produces a much, much wider beam on the wall. It's totally counterintuitive, but that is exactly how the world works at a quantum level. Section 3. Particle or wave. But just when you think you have this counterintuitive quantum behavior all figured out, there is a fascinating, slightly controversial debate regarding how we interpret it. Let's compare two completely different frameworks for the exact same physical event. On one side, we have the particle view, which we just walked through. This sees light as individual photons relying on Heisenberg's momentum uncertainty, causing those particles to literally veer off course because we constrain their physical position. But on the flip side, we have the wave view. As argued by Henry from the Minute Physics channel, this experiment might not actually be all that spooky. If you simply see light as a wave, then all the light is doing here is diffracting. Diffraction is just the standard phenomenon where if a wave passes through a slit, it bends at the corners and radiates out in all directions, like ripples in a pond. That wave behavior perfectly explains the spreading of the beam, making the whole thing feel a lot more intuitive.
And this forces us to confront a massive, foundational question. As the source material points out, that goes to the very nature of light. Is it made of waves or particles? This friendly debate over whether this simple laser demonstration is showcasing spooky quantum particle uncertainty or just standard wave diffraction, well, it strikes at the very heart of how we fundamentally understand the universe.
So based on this fascinating little laser experiment, we are left with the ultimate mystery to ponder. Both frameworks, the strict quantum particle math of Heisenberg and the smooth, continuous diffraction of waves, completely explain why the green dot gets wider on the wall when the slit gets narrower. But which is the true reality? When you strip it all down, is light fundamentally a wave or a particle? I'll leave you to think about that the next time you see a beam of light shining through a narrow crack in a doorway. Thank you so much for joining me for this explainer, and keep questioning the universe around you.